All right, so let's do chapter 3A, number 6. And really, 6 refers to the previous problem, which we did in our quad notebooks. So you have a line L, you've got a point M that's not on the line. How many lines can you find that go through M and never hit L? And what we said in class was there's only one that I can draw here. That's the one that's parallel. Let's see if it writes. There we go. So that's this one. So only one that's parallel. And then there are a bunch that are 3D type lines, you know, like if I drew one coming straight out of the screen from M, that would also not hit, but those aren't called parallel, those are the skew lines. So, what I'm going to write down here, remember this is called Euclid's parallel postulate. Which says I get exactly one line through M that is parallel to line L. Okay, remember parallel means it's got to be in the same plane. So the other ones are the skew lines again. So then we're going to take this idea here, this Euclid's parallel postulate, and use it in our proof for number 6. Okay, so for number 6 we need a triangle. So let me draw one here. Any triangle really, so here, I'll make mine kind of strange here. A, B, C. And we want to prove that that has 180 degrees in it. And so let's do a proof setup. Statements, reasons. And I'm going to start with and now remember this proof kind of involves some trickery here. So what I'm going to do is I'm going to get rid of these for 1 second. And here's point A. And now I've basically created the same situation that was over here, right, with the Euclid's postulate. I've got one point, and I've got this line. Well, if it keeps going on forever, it's a line down here. And so there's exactly one line that I can draw through A that's parallel to BC, right? And if I want to refer to this, I need 2 letters to call it, to be able to refer to it in the proof. So I'm going to put a D right there and say this top red dotted line is AD and the bottom one's BC. So now let me go back to black. So here, I'm going to say, let me make that thicker. And the reason I can do that is because of this postulate right over here. Euclid's parallel postulate. Okay, now let me put these back. There's one. There's the other, right there. Okay, so to make this problem a little bit easier, I'm going to number these angles 1, 2, 3, 4, 5. All right. So, what can we do with parallel lines? All right, we've got these parallel lines now. And in fact, let me mark that in the picture. These 2 are parallel. Now remember, anytime you have parallel lines, you can immediately start to think about 5 things. If you have parallel lines, then you get 5 different things. So one of those things would be corresponding angles are congruent. One of those alternate interior angles are congruent. Alternate exterior angles are congruent. Same side interior angles are supplementary. And same side exterior angles are supplementary. So really, anytime you have a line like this, you're going to then start thinking about these 5 things here. Okay, and see which ones help you. So in this one, I can tell that, let me get a different color. In fact, I'll do a highlighter for this. That if I extend this line right here, and I look at this part here, and this part here, right? Then if you look at those angles carefully, you can actually tell that angle 1 and angle 4 form a special type of angle, right? A special pairing. And if you can't see it, you can draw them by themselves. Here's 1, here's 4. And they're interior because they're inside these two lines, and they're on opposite sides of the transversal, so they're alternate. So this one right here, I can say, because parallel lines, these parallel lines right here, give me alternate interior angles that are congruent. And then if you look at this part of the picture on the other side, so I'm going to use this line again and this line again, but now I'm going to look at this transversal right here. Right? So using that same logic, if I redraw this one right down here, it essentially looks like this. Right here is angle 5, that's this one. And right here, up here is angle 3, that's this one. And you can tell it's that Z shape again. Those are the alternate interior angles again, and so these have to be congruent because these lines are already parallel. So and it's the same reason. All parallel lines give alternate interior angles that are congruent. Okay. Well, we're trying to get that the angles add up to 180. So in the picture, there are some other angles that add up to 180. And we mentioned in class, if you look up at the top, 1 plus 3 has to equal 180. And really what this is it's the angle addition postulate used a couple of times. What we said in class was it's okay for this one to just say, okay, it's a straight angle. We know those equal 180 degrees at this point. So right now I'm saying that's okay to write in a proof just for our class. Okay, well, now let's look. Okay, we just said 1 and 4 are the same thing in step 3. So instead of writing M1 here, I can write M4. Okay, M2 I'm going to keep the same because that's part of my triangle. The goal is to get these angles of the triangle all matched up. This one, and this one down here. Okay, so right now I've got that 1, 2, and 3 add up, and I'm going to replace the 1 with the 4, and I'm going to replace the 3 with the 5. So this one changes also. This turns into 5 equals 180. And so all I'm doing here is using substitution from step 3. And then we got one more step really, although you could say that we're done now. Because if you look at angle 4 is B, right? So this is really measurement of angle B. Measurement of 2 is really the angle A that's part of our triangle. And measurement of 5 is really angle C. That's not, I suppose you could say that's substitution too. It's really just replacing the terms with the numbers that we created. So I'll write substitution here. If you ended here, I'd be fine with that too, because that proves that the triangle has 180 degrees.